Alright guys, welcome back. It's another video from my beautiful new studio, looking nice and spiffy. I want to talk about a really important diagram in AP Chemistry, or chemistry in general. That is called the Maxwell Boltzmann. There we go. I'll toss another N on the end. I don't know if there's really two N's. Why not? I think it's a cooler name. It's a pretty cool name to start with, but I'll test another M on it. Diagram. There we go. Figured that out. Whew. Okay, well, may not be able to spell it, but I do know what it is. A Maxwell-Boltzmann diagram pretty much maps out the speed of a given number of particles. So let's say I have this right here, this right here. We're going to put... I'll put kinetic energy down here. When we think of kinetic energy, let's just think of perhaps temperature, okay? Or perhaps just the energy content, because that's going to become really important in a little bit. And then I just have here percentage of particles. Percentage of particles. Okay, so I have a Maxwell Boltzmann diagram. I have my percentage of particles here. I have kinetic energy. So let's say you have a pot of water or a balloon of gas or really anything. Not all those particles are going to be moving at the exact same speed. Temperature is an average of the kinetic energy of the particles. So some particles are going to be going very slowly. Some are going to be going really, really fast. And the majority of them are just kind of going to be just chilling. And we can graph that out in a Maxwell-Boltzmann diagram, and it'll kind of look like this. Well, that's fun. All right, and then if we were to take a temperature reading, of that pot of water or balloon of gas or whatever it is, this is what the temperature would read. It would read this. This is the average kinetic energy. Now, let's say, for example, let's back up for a second. Let me erase this, and let's talk about what it would look like if maybe we had different conditions, okay? We had maybe different conditions here. Okay, so here's my Maxwell-Boltzmann, my blank diagram. That's fun. Let me touch this up because that's going to annoy some people. Okay, so let's say I had a gas, a balloon of gas, and I got it down to 0 degrees Kelvin. All right, that's a pretty fantastic thing to do. I'd probably not be teaching at Richards. You know, I'd be, I don't know, making money somewhere else, selling my 0 degrees Kelvin gas or whatever it is. Anyway, so if I had a balloon of gas at 0 degrees Kelvin, probably wouldn't be a gas, but I would have just one spike right here, okay, because all my particles would have zero kinetic energy, because at 0 degrees Kelvin, all molecular movement is stopped, and there's no movement of particles. All of my things must have 0 kinetic energy. Right, and that makes sense, because if I had even one particle with energy, that would throw my entire average off, and I would have a temperature reading. So in order to be at 0 degrees Kelvin, absolute zero molecular movement, I must have all of my particles with no movement. So I would have a spike. Turns out, as I start heating up my gases, all right, let's say we have, I don't know, let's say it's a cold winter day. Let's say this is, I don't know, 7 degrees Fahrenheit. I know, I'm using Fahrenheit. Don't tell the French Système International police. Let's just kind of keep it on the DL. I use Fahrenheit. That's okay. So let's say I had a very cold winter day. My diagram would kind of look like this, right? Let's say it was a little bit warmer. Let's say it's a spring day. I know you guys can't picture that right now because we're kind of right in the middle of winter. One of the coldest winters around. Let's say that's 50 degrees Fahrenheit. Okay. Notice something, that as my gas heats up, the height of my curve goes down. All right, because initially it was bunched up at that 0 degree Kelvin mark, and now as I add energy, now it's not a big deal if some of my particles are a little slower and some of them are a little faster, because now I get an average. And the more I speed them up, the more that averages, and the more the nature of the particles changes. So, you know, let's say I heat it up even further. Okay? Let's say that's, oh geez, you guys are going to want this to scale. I don't know, 75 degrees Fahrenheit. Okay, so as I heat it up, the amplitude, or the height of my graph goes down. Now, I don't know why I dropped this fancy eraser to begin with, but I kind of need this right now. Okay, now let's say I have, let me just clean this whole thing up. Let's say I have a sample of gas. Okay, let's say I have a sample of gas. Just clean that up, there we go. And I wanted to do a reaction. So, wipe that down so it's not wet. Okay, so I have a sample of gas, and let's call the Boltzmann diagram this. Fun. Alright, so here's my average temperature right here, my average of all my particles. Let's say I want it to react, but the activation energy of the reaction is this. The activation energy of the reaction is actually right here. So when that's reacting, only these particles will actually undergo the reaction, because only these particles have the minimum amount of activation energy. And if we remember, activation energy is the energy required for a reaction to take place. So only these particles are moving with enough energy to actually react and cause this reaction to take place. Well, let's say I heat that up. And now let's say I heat up a sample of gas, and you're going to think, well, Mr. Wood, if I heat up a sample of gas, my particles will move faster. And if my particles move faster, they're going to collide more often. And the more often they collide, clearly, the more they'll react. And I will agree, that is true. But it is not the main reason why increasing the temperature speeds up the rate of my reaction. The main reason that it speeds up the rate of my reaction is because I will have more particles with the activation energy. Let's do this again. Let's say I heat up this gas, or this pot of water, or whatever it is, my solution. Let's say I heat this up. Let's say I heat it up like that. Now all of a sudden you'll notice my curve has broadened out because I heated it up, and when I heat up a gas, it broadens my curve. My curve is broadened out, but now take a look. All of this, I'm going to try and make this look a little bit different. All of this now is reacting. If you look, that's like 51%. You know, I believe in accuracy. That's 51%, whereas this is maybe only 25%. So by heating that gas up, the average temperature is right here. I'm not heating the average temperature up that much. But by heating the average temperature up just a little bit, I've more than doubled the amount of particles that could react. So this is a Maxwell-Boltzmann diagram. It shows you, based off of the energy, or temperature, or delta A, whatever you want to call it, based on the energy of the particles, and the percentage of particles, I can see that by just heating up a sample of gas just a little bit, I drastically increase the number of particles that have that activation energy. On the flip side, let's say I want to stop a reaction. Well, if heating it up speeds it up, well, let's cool that sucker down. If I cool that reaction down, let's say this is what it looks like. Now I have 0 particles with that activation energy, and my reaction has essentially ceased. They will collide, they will have the proper orientation, but they will not have the energy to overcome that initial barrier. Okay, so this was Maxwell-Boltzmann's a fairly simple idea. It's not a very complicated graph, but it is an incredibly important graph in chemistry. I hope you enjoyed it. I hope you understand it. There is a lot of nuances with the Maxwell-Boltzmann diagram. So good luck, and I will see you in class. Thank you.